Okay, well, we'll go ahead and get started. So the last topic that we're going to be able to get to this semester is the Laplace transform. And although it'll feel rushed because we are running out of time, the Laplace transform is one of the most important tools that engineers actually use. So a lot of the family-specific methods for differential equations, very few people use because A, you don't remember it, and B, since we're going to end up oftentimes in a numerical solution anyway, it's often easier just to go directly there. But sometimes it is important to come up with an analytic solution, closed form solution. And the Laplace transform is one of the methods that engineers actually use on a regular basis. And most people remember how to use this because they actually find it useful enough to use on a regular basis. So what is the Laplace transform? Well, we'll get to that here in a second, but I don't want to lose it in the big picture. The first day, I'm going to introduce you to the definition. How do you calculate the Laplace transform? And we'll do a little bit of practice taking the Laplace transform and the inverse Laplace transform. But what is it, and why do we use it? Transformations. Well, here's why we use it. It's an easy button. It will turn a very complicated mathematical procedure, the convolution integral, into a much simpler mathematical procedure, a multiplication. And it will similarly do that for many differential equations as well, because the differential equations and the convolution integral are intimately related in the study of systems. And engineers are very concerned about how systems respond to external excitation. So this is a critical notion in the study of systems, and electrical engineers call it signals and systems. There is a corresponding course in mechanical engineering. I can't recall what it's called now, but if you have a mechanical system or an electrical system, it has a certain characteristic, and that can be described by a differential equation in most cases. You have an excitation, an external loading, a wind. In the case of the circuit, you've got a signal that's coming into that. How does the system respond? That's generally answered with a convolution integral. And the convolution integral is a difficult thing to do out by hand. The Laplace transform makes it easier. It makes it a multiplication. So let me do a little bit of big picture stuff first, and then we will dive into the messy details. When you see transformation or a transform, there are a couple of reasons to do transforms. One is that they help you see things that you can't see or are difficult to see without doing the transform. So an example of that would be the Fourier transform, where you take a time domain thing, you put it in the frequency domain, and you can see frequency components of a signal. So that's one reason to do it. A much more kind of selfish or simple-minded reason to do transformations is for this, what I call the easy button effect. And just as you don't have to remember this, but this is a you should be on the lookout for transformations as you go forward in your academic career, because this is one of the things that a transformation can do for you. Imagine that you've got you have this kind of problem where you've got some set of inputs, okay, and this can be your problem statement. It can be anything that you want, but it's a starting point for your problem. And imagine that through some complex imagine that through some complex calculation or some complex procedure, you end up with the outputs. Okay, and this happens all the time, right? I mean, there are lots of times, in fact, that this is our business, right? We're given a set of data. We want to know what the answer is. We have to do some complicated thing to get there, and that's what they pay us for, right? Well, they pay you the same amount whether it's complicated or not. So sometimes what we do is we go through what's called a transformation. It's almost like a parallel universe, or it's completely equivalent mathematically, but for us it's easier. And so what we have to do is we have to transform our inputs. So there's a transformation. And once you get there, then there is a set of procedures, but they're much simpler. Calculation, not computation. That gets us some outputs. But now we're in this transformation universe, and we have to get back to the normal universe, and that's the inverse transformation. And there are several places in mathematics where we have this kind of alternate universe where instead of doing a complex calculation on the actual inputs, what we'll do is we'll take the inputs, we'll transform them into some other form, we'll do a simple calculation on them, get transformed outputs that we can then transform back to the regular outputs. So this is a detour, and the whole point of the detour is that the effort saved by avoiding this is enough that it justifies the transformation in the inverse transformation. So where's an example of this that you already know about? An example of this that you already know about are logarithms. And you may not consider them simple, but that's because nobody has ever asked you to do this by hand, right? Back in the day, when you had to do this, you didn't do this. Back in the day of the slide rule, what is a slide rule? The slide rule is a big logarithm table, right? And so what we would do with this is take the input, 741, we'd take the logarithm of that, which you would look up on a table, okay? And then what we would do, the simpler calculation is that a multiplication in the real world, this is a multiplication problem. You're asking yourself, what number x multiplied by itself 3 times is equal to 741? So instead of trying to figure out what number multiplied by itself 3 times is 741, what you did was you took the logarithm of it, you then realized that this is some other number, three times, okay? And so you would really just find the number ln of x, right? And then you transform it back and you'd have x. And if you don't believe me, that's what people did for generations. And I don't have my calculator with me, but if you had a table of logarithms, you could do this. The logarithm of 741 is, I don't know, about 9 or something, or yeah, something like that. And then you could do this, right? And you would think, okay, well, that's crazy because who's going to have a table for the logarithms? Well, and how is that any easier than doing this problem? Can't I just have a table of cube roots? Well, yeah, you could have a table of cube roots, but then the instant that I change this to this problem, now you got to have a table of fifth roots, but this approach still works, right? So you invested a lot of time in making a table of logarithms, and then you could use it for practically any problem that you wanted. And you would substitute for a complex calculation, multiplication and division, an easier calculation, addition and subtraction. And generations of engineers did this. That's why everybody had a slide rule. And that's also why in World War II, for example, one of the primary drivers for creating a computing device, a calculator, a computer, was to get more and more accurate, more decimal places in the logarithm table. And if you did that, then you could do all kinds of crazy stuff. You could calculate the trajectory of artillery shells, for example, or correct for the curvature of the Earth as you fired from a naval vessel, and so on and so forth. So these kinds of transformations occur all over in engineering and applied mathematics, and there's nothing wrong with them. They're actually valid. They're just clever hacks that somebody has found a simpler way of doing something, but they require you to transform from one domain, if you will, into another, do the simple calculation, transform back. What we're going to do is a Laplace transform. And what the Laplace transform does is it takes a function and it transforms it into a something. That something is another function of a different variable. And what happens is then that the complex calculation that you're going to do, which was a convolution, over here in Laplace land becomes a multiplication. Now, unfortunately, where this course falls in the sequence, you probably haven't done any convolutions, but trust me, they're painful. Have you done any convolutions? Okay. Convolutions.
It's been introduced in circuits 2, but I don't think we did any convolution problems.
Okay. Did you at least see what the integral looked like?
Yes. Yes.
Okay. Do you agree it's a nasty integral? It's a nasty integral.
Yes.
Okay, yes. So what we're going to do is we're going to substitute for this nasty integral actually a very easy calculation of multiplication, and then we're going to come back. Okay? As it turns out, this was the real reason to do Laplace transforms, but as it turns out, what this also does is it substitutes for not just a convolution, which is an integral operation, but integrals in general become a special form of multiplication. And because the real problem in differential equations is an implicit integration that you're carrying around in a big, ugly equation, is that turns solving ODEs into algebra. Because multiplying functions together is easy, and dividing functions is easy compared to integrating them and differentiating them. Okay? So this is what we're going to do, and this is the point. And I'm going to jump in, and we're going to do the definition of what a Laplace transform is. But here's the purpose. It's our easy button. We're going to avoid these operations, and instead we're going to substitute these operations. And our price is we have to learn to transform functions from this to that, and then transform the answers back. There are lots of these transformations that are floating around and that are used in applied mathematics and engineering. Fourier transforms are another one, and so on and so forth. You actually have seen this in power series expansion. There's sometimes when it's more convenient to work with the power series. So we take the function, we turn it into its power series, we mess around with the power series. We don't always inverse transform it back, but that's also a method that's used in differential equations sometimes. It takes recognizing the power series and turning it back into the function. Anyway, this is the sort of selfish, simple-minded reason to do transformations. There are other reasons to do transformations too. Like I say, the Fourier transform gives you the spectral content, the frequency composition of a complex time domain signal. And you can learn things about the signal or characterize the signal in a new way. But the reason that we're going to do it is for the easy button feature of this. Okay. So what is the Laplace transform? Okay, the Laplace transform takes a function and it turns it into another function. And that other function has certain characteristics that make it easier to work with for certain operations. Okay? And then we will do the inverse transform, which takes us back. Okay? So what we're going to do is we're going to transform into the Laplace domain, the S domain, and then do whatever it is that we're going to do, and then we're going to kind of come back. So today what we're going to talk about are these steps. How do we get there? How do we get back? You're not going to see the motivating reason for it, which is getting from here to here is easier than getting from here to here. Right? So, in fact, going all the way around is generally easier than going from here to here. And that's the idea. So let's talk about the Laplace transform. And what it does is it takes you from one domain, which is generally the time domain, t, into the Laplace domain, which is universally designated with an S. Okay. Why, I don't know. But if you see something that looks like this, they're almost always talking about the Laplace domain. You don't have to worry so much about the Laplace domain. I mean, some people do study functions in the Laplace domain, but you really need almost no results over in the Laplace domain to do the kind of analysis that you want to do. Okay, so let's study step one in this, which is how do you take a function f of t and turn it into f of s. Okay. This is the Laplace transform. And generally what we do is the notation for the Laplace transform is a big capital L with brackets, and if I take f of t and transform it, it will give me f of s. Okay, so this is just the notation. This says take the Laplace transform of f of t, and what will you get? You'll get a different function, and the function will be of s. Okay. So the definition for this operation and I haven't looked at your book. I don't know whether they use t or x. It doesn't make any difference. It's just that real problems tend to be in the time domain. Okay, so if your book says f of x, then just substitute t everywhere. Okay, so what's the definition of this? The definition, this is an integral operator. You have to do an integration on f of t. Okay? It's a special form of what are called, well, it'll look a little bit like a convolution, except it's not really. What it is it's taking f of t and the integral multiplies it by e to the minus s t. Okay, so this is the definition. All right? And what you have to do to get f of s is that for each s, it's a new number in here, right? So this defines a function. But for the purposes of the integral, since it's with respect to t, the s is just treated like a constant. Okay, so this integral is not so bad. It's a reasonable question to ask, is this integral going to exist? And the answer is that it usually does. Usually is not a good mathematical term, but this thing goes to 0 so fast that for the majority of well-behaved functions, f, this integral is going to exist, and that's going to give you your Laplace transform. In particular, for piecewise continuous functions, meaning that f of t can have discontinuities, but it can only have a finite number of discontinuities. And what we call of exponential order, that is, that this product goes to 0 as t goes to 0, or t goes to infinity. This product goes to 0 fast enough. Okay. So the restrictions on f of t are that it's piecewise continuous and that it's of exponential order. Which does have a precise mathematical definition, but my definition for you guys will simply be that this does not blow up faster than this goes to 0. Okay. So this doesn't have to go to 0. It can go off to infinity. It can be x squared, x cubed, x to the 15th, or something like, or t to the 15th, for example. But that's not so fast that e to the minus st. E to the minus st will still, when they're multiplied together, force it to 0 fast enough. That's what exponential order means. Okay, so this is the definition. The definition is in itself not very useful, but we're required to play with it a little bit. So today what we'll do is we'll take some of these, we'll apply the definition. Okay, so the definition, you should be familiar with it, be familiar. But actually, and you'll have to be able to apply it. I'll ask you some questions about applying it because it's on the state syllabus. But for the most part, when you actually do the easy button method, you'll use a table. Okay, so the definition is only of limited use. It's for test purposes. In practice, you will simply use a table. All right, but for test purposes, let's do some examples. Okay, so the very first thing that everybody does is the Laplace transform of the function 1. Okay, so here f of t is the constant 1. Right. So what does that look like? So what we do here is we simply apply the definition, which is the integral from 0 to infinity. 1 times e to the minus st dt. And this thing has a pretty simple integral. This will be 1 over s minus sign in front of it. Okay, evaluated from, oops, sorry, e to the minus st, evaluated in t from 0 to infinity. So what is this? This is minus 1 over s. Okay, when I let t go to infinity, this thing goes to 0. And when I put 0 in here, this thing goes to 1. Okay, so now I fix my negative signs, and this is simply 1 over s. Okay, and this will be an entry in your table. Okay, so let me stop there. This is a simple-minded example, but any questions? This is the definition. What you have to do is you have to take whatever the function is, multiply it by e to the minus st, take the integral of that product, and whatever the integral gives you, that's what the Laplace transform is.
You may have actually already mentioned this, but we were using e to the xt because the rules of math are a little bit, or the operations anyways, the mechanics of it are a little bit different for those.
Yes.
We're doing the
there's a whole family of transformations of one function to another that involve this kind of thing, where there is some function that we multiply by our original function, and we get a transformation out of it. This is what's called a kernel. And there's a whole family of these things, and they each have different properties. Laplace studied this one where this is e to the minus st, Okay, he studied this one kernel and found, yes, important and interesting things that occur in this new domain. Primarily what occurs in this new domain is that the integral operation of convolution becomes a multiplication. And that's enough of a savings that it's worth transforming our f over there, doing stuff, and coming back and coming up with our answer. But if you're interested, there's a whole family of transformations with different functions. This thing can be different, and like I say, it's called a kernel. It's a
based on the type of transformation we're doing.
right, whatever you want. And for our purposes, it's e to the minus st.
Okay.
Okay, so and you know, in terms of our schematic that I had before, this is the hard world, and this is the easy world. All we're doing right now is we're doing this transformation. Okay, and then we will learn how to do this step and this step in a little bit. In fact, today we'll do this step and this step, and then we'll worry about that step later on. Okay, so very first Laplace transform of the constant function 1 is 1 over s. All right, well that's good, I guess. I don't know what it means, but it's good. Let me give you some properties of the Laplace transform that will come from the definition. Properties are that the Laplace transform is a linear operation. What that means is that when I take the Laplace transform of C1 times f of t plus C2 times g of t, here's a linear combination of two functions. If this transform operator is linear, then here's what I should get. I should get a linear combination of the individual Laplace transforms. Okay, and this is true. Okay, how do I know it's true? Well, I just show it. So this is, what is this thing? Okay, so here's my statement and here's my justification. So the justification for this is, what is the Laplace transform of this? Well, by the definition, it's this thing. Well, by the properties of integrals, you know that I can break this up into C1 integral 0 to infinity f of t e to the minus st dt plus C2 integral 0 to infinity g of t e to the minus st dt. And what is this? This is C1 f of s plus C2. So it is linear, and that's good because we're going to be applying this to linear systems.
So eventually when we go back, then will our rules of, I assume we're going to be taking a derivative, but will those rules also change because we're going to transform?
Yes, you're going to transform back, but the transform back is actually easier than you think.
Okay.
Because what you simply are going to do is you're going to let's say that you have an f of s and you want to get back to the f of t. Mm-hmm. Then what you do is you look in your table, the pattern, you match that, and then you simply look back.
Okay, yeah, I got it.
In theory, you could differentiate and get back, but we're actually not going to do that.
It's easier than that.
Yeah. Nobody does that. Everybody goes to the table.
Maybe I want to differentiate.
Just kidding. Okay, so what do we know? The Laplace transform is a linear operation. Okay. What significance is that? Well, now you already know this, for example. What is the Laplace transform of the constant function c? A second ago we did, well, what is this? This is the Laplace transform of c times 1. Okay. Well, I know what 1 is, right? So this is C times the Laplace transform of 1. So this is C times 1 over S, is C over S. So this is, you will start to be building your vocabulary of Laplace transforms just like this. Okay? So we started with a 1. We observed that the Laplace transform is linear. As a consequence, now I know the Laplace transform for every constant function C, and it's just C over S. Okay. And all I'm doing is playing around with the definition. I'm not doing anything significant yet. Okay, so that's good. By the way, the Laplace transform as a linear transformation is something you're going to be using so often you'll forget that you're even using it. So that's not such a big deal. Let's do the Laplace transform of t. Okay. So what happens when I just want to do the Laplace transform of t? Well, I don't know. I apply the definition. Okay. I have to integrate this. Either you remember how to integrate it or what technique of integration do you use?
By parts.
Yep, this is a by parts. So you let u is equal to t, so that du is equal to dt, and let dv equal e to the minus st, so that v becomes minus 1 over, okay, so that v becomes minus 1 over s e to the minus st. Okay, so then this whole thing then becomes uv, and remember we're taking this 0 to infinity. So I have to evaluate this thing, uv, which is minus 1 over s e to the minus st times t, okay, minus integral v du, v I have to change the variable x, that's fine. V du okay, and now t goes from 0 to infinity. Okay. All right, so I let t go to an infinity here. I'm really confused here. All right, so that. Okay. Sorry about that. So now I let t go to infinity, right? And when t goes to infinity here, this thing goes to 0. What's this thing? This is plus 1 over s integral 0 to goes to infinity. Okay, and then I put 0 in, and then 0 to 0 is just 0. Okay. So the only thing left is this term. Okay, and when I integrate that, right, here's what I get. I get 1 over s squared e to the minus s x, negative sign. That goes from 0 to infinity. Let x go to infinity, this goes to 0. Let x equals 0, this goes to 1 over s squared. So that's the Laplace transform of t is s squared. Okay, and I'm going to write that down over here. In fact, I'm going to start my little table here. There's a table, by the way, now on the website, and hopefully you also have your book, and we'll use the table here in a second. But here's what I know so far. Here is f of t, and here is the Laplace transform f of t. Okay. The first entry up here is, well, we'll do c. Okay, the Laplace transform of that is c over s. This one tells me the Laplace transform of t is 1 over s squared. So I guess I could say, for example, ct is c over s squared. Okay. All right, let's see what happens when I now look at the Laplace transform of t squared. And yes, there's a pattern here, so we won't be doing a gazillion of these. We just have to do it enough to find what the pattern is. Okay. Well, this is also integration by parts, but it's integration by parts twice. Okay. So in this particular case, I'll let u is equal to t squared. Du is equal to 2t dt. V dv is e to the minus st dt, and v then is equal to minus 1 over s e to the minus st. Okay, so if I do all of this, then what do I get? Okay, I need uv, so this is minus 1 over s t squared e to the minus st. That's u times v, minus the integral v du, so this is minus 1 over s, integral 0 to t, v du, v du, and that's evaluated from 0 to infinity in t. Okay, so when I substitute in here, and this will be integration by parts again, but you'll notice that this is the integral that we just found. In particular, it's this one. But let's go through the motions here, and we'll put in, we'll let t go to infinity. This thing goes to 0. This thing goes to 2 over s, integral 0 to infinity, e to the minus stt dt. When I put in 0 here, this whole thing is 0. Oops. When I put 0 in there, I get 0. Sorry, these are all x's. All right, and then what is this? This is 2 over s f of, this is the Laplace transform of t. Okay, what is that? That's 2 over s times 1 over s squared. So this is 2 over s cubed. And what you'll find is if you keep doing this, if you do t to the n, what you get each time is the n term coming down and multiplying it. So when it's t squared, you get a 2. When it's t cubed, you'll get a 2 times a 3. When it's t to the 4th, you'll get 2 times 3 times 4. Okay, so this is in the numerator n factorial, and in the denominator it's s to the n plus 1. And like I say, I mean, the big thing is that you're able to use the definition. Most people will have a table. Okay? So there should be a table in the back of your book. somewhere.
We'll put it online.
In any event, there's a table on the Blackboard website in the folder for this week, and that will be the table that I'll give you for the exam. So you want to print that off. Okay. I'll only give you the front page. The back page has some notes. Okay. All right. So if you keep putting it to a higher and higher power, what you'll find is you'll get n factorial over s to the n plus 1. Okay, so far, all right, this is fine. There's nothing terribly exciting about it. But there are some useful things suggested by this next Laplace transform. Here's the Laplace transform for differentiation. Okay, so if I take the Laplace transform of the function f prime of t, so imagine that I'm taking the Laplace transform of the function. It's actually the derivative of some other function. And let's suppose that I do this. So what will this turn into? This is the integral 0 to infinity, again from the definition, e to the minus st f prime of t dt. Okay. Now, apply the method of by parts to this, okay, just for fun. So for example, let u is equal to e to the minus st. If you do that, then du is equal to minus s e to the minus st dt. Okay, so far, nothing, no rocket science. But if dv is equal to f prime of t dt, then v is just f of t. So then when I do this integration, here's what I get. Okay, it's uv minus the integral 0 to t. This time I will change the variable. I will change the variable. V du. Okay, so this is plus s e to the minus s x v f of x dx. Okay, and that's evaluated from 0 to infinity in t. So let's see what this does. When I let t go to infinity, this goes to 0. So I get 0 plus s times the integral of 0 to infinity, e to the minus s x f of x dx. Now I put 0 in, okay, minus. When I put 0 in, this becomes a 1, this becomes f of 0. Okay, and this thing becomes the integral from 0 to 0 over 0. Okay. If you look closely, this is s f of s, and this is the initial condition minus f of 0. So the Laplace transform of a derivative is the Laplace transform of the undifferentiated function times s. So this is what I'm saying, that differentiation in our normal time domain becomes multiplication in the Laplace domain, multiplication by s. And in general, there's a more general form for a higher order derivative. So I'll just write that down. You can do successive transformations if you want to. But here's the first derivative case. Here's the nth order derivative. Okay. So the nth order derivative looks like this. If I take the Laplace transform of the nth derivative of a function, what I will get is that function's Laplace transform multiplied by s to the n. Basically, you get a polynomial in s. You get s to the n minus, let's see, s to the n minus 1, f n minus 1 at 0, minus s to the n minus 2, f n minus 2, and so on and so forth until you finally get to f of no derivatives. So you'll get this big long change, and these will all be initial conditions, so there'll be numbers that you actually know from elsewhere in your problem. But the nth derivative is the multiplication by s to the n.
Oh, I think. You don't see this. It says something a little different than that.
Did I mess up the sign?
Just the n minus 1 above at the f.
The derivative. Where's the derivative on
It's
here?
all at the bottom.
Oh, it's at the bottom, yeah. Oh, I have them in the wrong order. Yeah.
Well, let's see, it's like reverse. So you have s in minus 1, f in minus 1. It should be.
Yeah, it should be the other way around. Yeah, okay. So this, I have it in the wrong order. Again, you'll go to the table for these. So this is f to the 0. This is f to the. This is the first derivative, and so forth. This is the n minus 1 derivative. All right. Yep. Sorry. In any event, these are all terms that are going to come from your initial conditions when we apply this to differential equations. The big thing to remember is that this is true. This is the multiplication by s to the n. Okay, so your nth order differentiation is replaced by multiplication by s to the n. And this is, and its analog, which is the integration is division by s. This is the basis for doing algebra instead of differentiation and integration. Okay. Does everyone have access to a table? Because we're going to do some of these in a little bit. Let me do one more, and then I'll ask you to do a couple of these, and then we'll go to the exercising the table. So sorry about that. Any other questions or comments about these applications of the definition? Apart from having to go back and do the techniques of integration, is it clear what we're doing? Maybe not why we're doing it, but is it clear what we're doing?
Yes.
Okay. Okay, so let's take a look now at a couple more. One that you may not think is terribly important, but is hugely important, is translation. This is very important. If I do this, the Laplace transform of e to the, let's do at times f of t. So take a function, then multiply it by an exponential. The question is, what is that? Right? well, let's apply our definition. That's just going to be e to the minus st plus e times our function, which is e to the at f of t. Okay. And now you can see what's going to happen here. What we're going to get is this thing, integration from 0 to infinity, e to the a minus s t f of t dt. And this is not a change of variable because these things, the a and the s, are just constants as far as this goes, because we're differentiating with respect to t, or we're integrating with respect to t. So this is just a constant. This is a number, just like as before. So when I do this integration, what I get is simply needing to change my variable from s to a minus s. Right? So what I'll do here is, for example, let sigma, Greek s, equal to a minus s. Right? So then I get this integral. This is just a bookkeeping technique. Okay. Actually, what I need to do, I'm sorry, I need to make it equal to this. To fit my definition, I need a negative thing here. I've got a positive, so I just need to fix that. So yeah. So put a just to make the notation a little better, I'm going to take out the negative sign here, and I'm going to make s minus a, like that. And so I'm going to let sigma equal s minus a, so that this thing becomes negative sigma t. Now this looks just like that, and so what I should end up with is the Fourier transform, not in s, but in sigma. And then I just replace it with that, right? So this is actually the translated version of the original Laplace transform. So this is a translation in S. Okay. We will also do a translation in T, which is a little tougher. But both of these should be in your table. This is a translation in S. Sometimes it's useful. But what this says is, if you want to translate in S, then you multiply by e to the at. Okay. All right. So these are some of the things that we're going to end up doing. Let's try. Let me ask you to try one of these, which is just using the definition. Okay, so let's do exactly this, right? Except try applying that to this. So we already know what this is. But you can do that either with the definition or a substitution into to what you know down here. Okay? So set that up for me and get as far as you can, or work it if you can, and then we'll do it together. And again, all we're doing here is we're exercising the definition. So maybe I should say that. Use the definition. So let's go ahead and work this together. So I should have put this as the stipulation in the very beginning. So use the definition. I'm supposed to make you exercise the definition. So on a test or quiz question that I want you to do that, I'll always say use the definition. Right? So if I ask you use the definition to find the Laplace transform of t e to the at, what would you do? How do you set this up?
Integral.
Okay, so the definition is that integral operation.
Yeah.
Good, right?
From e to the at.
Okay.
E to the minus st of t dt. Well, times t dt.
Okay, so there's a t in here somewhere, but it doesn't matter where you put it, right? So, okay. So what do you need to do? Anytime you need to use the definition, you take whatever function it is and you put it as a product with e to the minus st, and you take that improper integral from 0 to infinity. All right, and now it's just integration, right? And so this is 0 to infinity. Probably group these together. So this is t e to the a minus s t dt. Okay. And, you know, again, you can either remember what this integral is, or you can do it by parts. It's simple to do by parts, so we'll do that just to keep track of everything. So you would let u equal to t, so the du becomes dt, okay? And then dv needs to be e to the a minus s t dt. And then I integrate that, so the v is 1 over a minus s times e to the a minus s t, right? Okay. So then this whole thing becomes uv, right? So this is t times 1 over a minus s e to the a minus s t. Okay, that's uv minus the integral from 0 to t of, and I will remember to change the variable. I always forget to change the variable. V du. Okay, so this is 1 over a minus s e to the a minus s t, okay, du. Oops, I will remember to change the variable. And that goes from 0 to infinity, right? In t. So if I didn't screw that up, that's what I should get. Now, what is that? Plug in infinity, okay. Well, e to this number, not clear what it does, right? What has to happen is that what you have to know is that for if s is greater than a, then this is negative and will go to 0. If that's not true, then this whole thing blows up. So we're going to have to restrict this to s greater than a. All right. If s is greater than a, then this goes to 0. And so that's good. Then I have minus the integral from 0 to infinity of 1 over a minus s e to a minus s x dx. Okay. And when I put 0 in here, then this goes to 0 and it doesn't matter. I put 0 in there, it goes to 0 and it doesn't matter. So this is the only term that I have left. But I do have this restriction that s be greater than a. Okay. All right. And then all of this stuff then becomes 1 over a minus s squared. Okay. E to the a minus s x, and evaluate it from 0 to infinity. All right. And then finally, I have to plug these things in, right? If I put 0 in, that's the only term that's left because this goes to infinity again. For s greater than a, this will go to 0. All right, so finally what I'm left with is 1 over a minus s with a minus sign in front of it squared. All right, and usually I don't think that's the way that they write it. Usually they write it the other way. But that's also a translation in S.
Yeah, they write it s minus a squared.
All right, so why?
If you come off the table.
Right, and so why does that not matter? Okay. Well, because the square changes the sign, so it doesn't really matter what order you write those in. But where does that negative sign go? All right. All right, I'll have to puzzle that out. I'm not really sure where that negative sign goes, but we've done the thing the right way. Let's see. That negative sign comes right here. That looks right, but nevertheless, anyway, the order that you write this in doesn't matter because the square takes care of the sign. So it doesn't matter what order you write that in. The question is, what happened to the negative sign? And I'll have to find that out because I'm not seeing it right now. But the answer in the table is the correct one, which is this should be s minus a squared. And the idea here is that when you multiply by e to the a, what you'll get is a translation in s. So you started with this form, 1 over s squared. Okay? And the translation in s by a just makes it s minus a. Okay? So that's where that comes from. And where that negative sign comes from, I don't see where I'm losing it, but we'll do that. I'll find my error by Wednesday, and I'll show you that. Okay. All right, but the use the definition part is can you take this, can you plug it in, and then can you work the integral? And that's all. That's all we're really asking you to do. Okay. All right. Now, what we want to do is we want to use this table, and I'm glad that you have a table. Everybody has a table in front of them. It's there's one on the back of the book, and you should print the one off out of the folder for this week. Okay. Just to get used to it. The tables are all pretty much similar. Okay. So just get used to the one that's in the Blackboard folder for this week. You'll see a bunch of things that we probably won't use. The things that we will use, however, are the Heaviside function. But I'll tell you what that is later on. It's also useful if you've got in physics you'll often find the delta function, and this allows you to work with the delta function too. That's an integral operator. Okay. So there are lots of places where the Laplace transform helps you. What I want to do now is I want to practice using the table, because using the table is actually, as you saw with the table of integrals, is a little more complicated than just looking something up. So let's take a couple examples. And I will figure out what I did wrong with this one. The tool from algebra that you'll need doing this, that you may have forgotten, is a partial fraction expansion. So if you've forgotten how to do partial fraction expansion, or if it's been a while, it's worth reviewing. So go back and review partial fraction expansion. What is partial fraction expansion? If I have an expression like this, like s plus 1 over s squared plus 3s plus 2. Okay, well, I don't want to do that one. Let's do this. S plus 5. Okay. Let's say that I have this expression. The problem is that you're not going to be able to find this in your table. Right? So to find an expression in your table, you're going to have to do this. You're going to have to factor this into its component parts. This is s plus 1, s plus 2. Okay. So you will expand it into its partial fractions, the s plus 1, s plus 2, and you'll put an a here and a b here. And you'll find a and b. Right? Because once you do that, then you're able to look this up in the table. You'll have an entry for these where you didn't have an entry for that. We can do this one, but let's just go ahead and do some examples. And we will practice using the table. Okay. So this is what partial fraction expansion is. It's going to be the one tool from algebra that you may have forgotten how to use. So let's try using the table some. In your table, and so for the inverse Laplace transform, it's by the table. And what you do is you take your function, whatever it is in the Laplace domain, and you find its pattern on the table. Right? And you simply use the table to get back. And it's usually just some algebra that you have to do. So for example, let's try, and the notation is something that looks like this. What you're doing is you're taking a function in S, and you're trying to move back to a function in T. The notation to do this will be this, inverse Laplace transform. And that will give you your function in T. So that's a notation for finding the inverse Laplace transform. And you could, in theory, do a differentiation operation to get you there. Nobody does. Everybody uses a table. And the reason you're able to do that is that if you find the function whose Laplace transform that is a Laplace transform of a function in T, then the inverse Laplace transform of that function is the function in T. There's a uniqueness theorem that we're going to have to apply to use that. So for example, how is this done? They might give you something like this. What is the inverse Laplace transform of 1 over s squared minus 48 over s to the 5th? So here's an example of finding the inverse Laplace transform, and you'll be using a table. The table entry that we're going to want to use, if you're using the same table that I am, is this one. And if I can find it. It's number 3. Okay. So the table entry that I'm looking at is on the one I'm asking you to print out. is this. T to the n is equal to the Laplace transform of this is n factorial s to the n plus 1. So that's the Laplace transform that we're going to use. And we're going to use it twice. Okay, so the first thing we do is we recognize that there's a linear property here, that this thing is equal to the inverse Laplace transform of 1 over s squared, okay, minus the inverse Laplace transform of 48 over s to the 5th. This is the inverse Laplace transform still of 1 over s squared. And I need, it looks like 4 factorial. In the numerator, 4 factorial is 24. So I need the inverse Laplace transform of 24 over 5, s to the 5. But I have 48, so that must be 2 of those. Okay, and then so finally, this is just the function t. Okay, and this is the function t to the 4th, so minus 2t to the 4th. Okay, and so what you're going to do when you take inverse Laplace transforms is use the table, make it match the table. How do you make it match the table? You use the linearity property to pull out constants, right? And you mess around with it until it works that way. Okay, let me pause there. Does that make sense? If I have this in my table, I know that the Laplace transform t to the n is n factorial over s to the n plus 1. Which means that the inverse Laplace transform of n factorial over n to the s to the n plus 1 is t to the n. You would apply it to each one of these terms individually and come out with the inverse Laplace transform. Okay, does that make sense? Let me do one more really quickly, and then we'll call it a day, and we'll do many more of these later. Let's try. Let's try one of these partial fraction expansion ones. Do the, let's do this one together. Inverse Laplace transform of 2s plus 2 over s squared plus 6s plus 8. What you'll do is you'll take a quick glance through your table. You won't find anything that matches s squared plus 6s plus 8 in the denominator. So what we're going to do is we're going to turn this into something that looks like this. This is s plus 4, s plus 2. Okay. And I need the numerator. Okay. How will I find the numerator? Well, I need to do partial fraction expansion. So this is 2s plus 2 over s squared plus 6s plus 8 is equal to a over s plus 4, b over s plus 2. And what is this? This means that a s plus 2a plus b s plus 4b over s squared plus 6s plus 8. Right? This thing has to equal that. Right? So what does that mean? That means that that means that a plus b is equal to 2, 2a plus 4b is equal to 2. Right. And you would just solve this. Right? So I'd subtract 2 of these from that. I get that 2b is equal to minus 2. Okay, so b is equal to minus 1, and that means that a must equal 3. So this is 3 plus minus 1. And you can look in the table now and find the inverse Laplace transform of each one of those. If you need to go, I apologize for running over. Let me just finish this and we'll be done. So I look in the table, and what does that tell me? The table entry is this one. Which I think is 23. Okay, so the table entry says that t, that e to the at, okay, is going to be 1 over s minus a. Oh, it's just e to the at, sorry. Okay. All right, so this is going to be 3e to the minus 4t minus e to the minus 2t. So there's the inverse Laplace transform. Okay, so I apologize for going over. We need to, oh shoot, I lost on. We need to decide when we want to do the exam for this, because it's going to control how much information I'm going to be able to cover. So by Wednesday, please decide, do you want to roll exam 4 into the final and not have a separate exam 4? Do you want to do exam 4 at the end of next week and then have the final week for just the final? Or do you want to do the exam 4 on the Monday of finals week and then the actual final on the Wednesday through Friday?
This would be either way. This would be covered on both the final and
Yes.
on this.
Yeah.
But I would personally prefer to do this as soon as possible. That way,
Separately as like
And then-
next Friday?
so next Friday would work, because then because then whatever additional information we get, we can put that also on the file. Like it was like.
Okay. What do you think, Jacob?
I agree with that. I would like to have a test over this next week before finals week.
Okay, so then that's what we'll do. So it'll be available in the testing center Wednesday through Friday. There'll be a quiz on this coming Monday, and what the quiz will be over is not the whole business of the Laplace transform, because there'll be a little bit more stuff. But it'll definitely exercise the definition, and it'll be using the table to take the Laplace transform and the inverse Laplace transform, and we'll talk more about it on Wednesday. So that's what you'll miss, Jacob. But there should be a video, okay, and I'll put some sample problems in. Right?
Okay.
Okay, and then next week we'll probably, by Monday, we'll be talking about actually using it to solve differential equations.
So
Okay.
quiz Monday, exam Friday,
Exam
finals
Friday.
next week.
Or Friday.
Final the week after.
Yeah, the week after.
All right.
All right, thanks very much.
Okay. Thank you.
It's interesting. I've used the Heaviside functions someplace at some point in time.
Yeah, I mean, most people just call it the step function, but yeah, it's an important tool to window.
I mostly remember the word.
Yeah.